All right, so in this podcast, we're going to talk about, we start with the concept of unions as a set concept, right? And in this notation, it essentially just sort of says, we can make a set by taking two sets that already exist, like X and Y, and we can union them together. Like X could be all the odd numbers, Y could be all the even numbers, and we can, take the union and we'll get all the whole numbers. Or whatever that you get that concept right. Um, so what we do then in set theory we call that unions, and in programming languages we call it union. So here's an example in C on the left that shows the declaration of a union that we're going to call element, and we're going to define it to have an int part and an f part. And ML very similar. You got that kind of or symbol in the middle. And but what's interesting about the way this works in languages like C, and I think it works the same way in ML. Essentially, it looks like a record, right? You want to say that there's an element and it's got an I and it's got an F, but it doesn't. It actually has an I or an F, and it occupies a spot that is essentially as large as the biggest one of the two. Okay, so obviously float's going to probably be bigger, probably occupy more bytes, and so it's going to be every one of these elements in the union is going to be um, the size of a float in the case of C, right? And the size of a should be a real in the case of ML. So that's kind of one thing to just kind of keep in mind. In essence, the representations overlap each other, and this is a little scrungy. But what I want you to kind of see is, in this one you've got this I, which is an integer. You've got a pointer to character, right? P is a pointer to a byte or to a character, and then we declare this variable U, right, of this type union element. And then as a note that again, if you're rusty with your C comments, this is just a comment that the size of U is equal to, you take the size of U dot I and the size of U dot P. Bigger one of those is the size of that variable. Okay, and so just kind of something to keep in mind. Depending on the language, we've talked a little bit about this in the other podcasts, but the representation might be exposed. You might have access to that, or you might not. And there's a little thing we want to kind of touch on here in a second that kind of relates to that idea. So there are, this notion of strictly typed unions, and this example is an example in ML, okay, where all you can do is just extract the contents. And so what this is, and I just have to apologize because this code, I'm kind of this time around just following the author, and he's introducing language things like of, which is a keyword that doesn't show up for a little while in the book. So we haven't even gotten to this part yet. So in that respect, don't worry about that because we're going to get to it. But what I actually did is I was kind of playing around with this. You got that data type element, right? And that vertical bar, the or sign, tells us I've got I of int and f of real, and I was just kind of confused because I was looking at get real, right, which wants f and x, and it returns x, or I and x, and it returns real of x. I'm like, what in the crap? What are we doing here? What is that doing? And I don't have it here in the slides, but if you do this, just jump on SML and just put this stuff in, and then just sort of see what the types are. It actually tells you that f and I are functions, and which kind of changes the game a little bit in ML. So then what I did was, when I called, and this is not in the book, but when I actually called get real, and then just said, I 23, and then I called get real with f 23.3, which is clearly a real number. What I got was a value. When I did get real I 23, I got 23.0. When I did f 23.3, I got 23.3. And if you think about it, what I've got is it's gonna return a value back to me, right? So again, looking back at the code, I've got I and I've got F, and those words are actually like known and remembered in ML. Once having defined that, I and F have meaning, okay, outside that context. And that's kind of the little bit of syntactic sugar that I figured out, because it wasn't really obvious in ML. Um, but anyway, in other words, if I do get real and the values are real, I just return the value. But if I do get real and the value is an integer, right? I go I and then an integer. Yeah, then I actually convert that into a real and I return that. You'll see it if you try that. Um, and then this is just kind of an interesting one. This example is in C, but the notion that we have varying degrees of exposing, the details, right, of the implementation. And okay, so this notion that programs can take advantage, of this idea that I can see into the representation is again, C is the most notorious language in terms of really popular languages that let you get away with all kinds of junk. And in this case, I've got a union element, I've got an integer, and I've got a float, right, called INF. And so I can do this. I can declare E as a union element, right? And then I can assign E dot I to be 100. In other words, I'm just putting I into it. Now remember that the space I've allocated for every one of these elements is the size of the largest one, which in this case will be a float. So even if I'm shoving a value into the integer portion, it's like the rest of it's just kind of padded, and I don't care because I'm just treating the integer part. But then if I just turn around and then declare this variable x and make it a float, and then I just assign it to be e dot f, then in C I can like get that back, and I can actually basically it's like a roundabout way of performing a cast, where I can take that clearly integer value, and then when I'm pulling it out of F, you're like, okay, how does that work? Well, because it's so loosely typed that when I'm rolling, when I'm actually executing, it's not going to complain. It's like, oh, you want to treat that union as if it's the F part? Fine, you must know what you're doing. You're a professional, and that's So it's just an example of a weird little programming trick that's accommodated by C. And again, I don't know exactly why you'd want to do that. There's probably some reason. It's a cast, effectively, right? So you kind of get the idea. So here's what I did another one of the other podcasts, right, where we talked about ANSI C. And again, just to give you the illustration that you have to get these specifications nailed down in Kernahan and Ritchie, the C programming language. We've got this thing again, right? A union is a structure, et cetera. Everybody starts at 0. And this just gives you, the details aren't that important other than to say, um, that there are rules that govern what we're going to care about, what's going to be loose and what's not, depending upon the specific language. And so there's one other thing we're going to talk about here in this portion about unions, which is this kind of we call it a discriminated union, but this notion of variant records, okay? And frankly, this is a little bit esoteric. It's not the kind of thing I'm going to care about deeply, but it's not a bad thing to at least have a moment, okay? And the author provides an example, and I believe this example, if I'm remembering correctly, is in Ada. Yeah, it's in Ada. And what we do in this example, so again, it's Ada. I'm not an Ada programmer, so I'm kind of we'll do our best here, right? So I declare a type called device, right? And it's an enumerated type. So I say that this device is, it can be a printer or it can be a disk. And thank you, Ada, for all the capital letters. Then I declare this type peripheral, and then there's a unit which is of type device, that enumerated type, okay? And then I declare this thing to be a record. And again, I know you're not going to go look this up in Ada or go find an Ada compiler. And then I declare, a field called hours working. And then I declare, I do a case where if the unit is a printer, which is one of the two enumerated types of device, or if the unit is a disk. So if it's a printer, then I declare a variable called line count. I make it an integer. But if it's a disk, I have cylinder and track, 2 integers. So you can see that that's a little bit like a union, right? In this kind of variant record, but really it's sort of, I view this more as like, I think it is a union, but it's more of a union where like you have to do all the heavy lifting and the language doesn't really make it super smooth for you, right? The language, it's just you can do a case in the middle of a type definition, which is, we're used to putting cases, in switch statements and things, but I can put a case in Ada in the middle of a type definition and effectively, allocate more space if I need it when the type is disk, and less space if I don't need it when the type is printer. And, just an example, of another kind of roundabout way of making that work. And so that's the end of what we have to talk about relative to unions. The next thing that we're going to be talking about is in the next podcast is subtypes, which I think is actually a fairly important concept.